Okay. Chromatography as an umbrella is really was invented or discovered, as whatever, however you want to look at it, about 1850. And that first person's run and looked at the separation of dyes, colored dyes, using a chromatographic method. 1906, it got found its way into plants and potentially foods. Separation of plant pigments, so colorants in plants. 1941 is kind of the first theoretical gas chromatography. So we have a gas as the mobile phase, like say a coating on the inside of a column. That's supposedly our liquid. So in 1941, they said, this guy, Martin Syringe, said, hey, I think we can do this. This works. We do liquid, liquid. We can do gas, liquid. And so they kind of set up that system. In 1954, they had thermal conductivity detector, TC, thermal conductivity. And so that's kind of been an evolution from that time. At this point, it is a mature technique. There's no other advances that can be made in it to do better separation or better detection. It's what we call a mature science. So if you might look at something 10 years old, 20 years old, or even up to 30 years old, it's kind of exactly the same thing they're doing today. It doesn't, it's, like I say, it hasn't advanced scientifically over that time period. And so what we'll do is we'll go through it, like I say, in parts. Gas chromatography. Yep, mobile phase is a gas. We'll go through what gases there are. There's a difference in gases and how they perform. So your mobile phase is a gas. Your sample must become a gas. So it gets trapped and or moved along that gas that's flowing through the column. And so you need to be able to vaporize your sample one way or another. You kind of look at sugar and you think, sucrose, how much would we have to heat that to get into gas phase if we want to separate it? Decomposes before it evaporates. And so in those cases, you actually make some kind of a derivative. So you can make a solid material or a liquid material into a gas by making some kind of a derivative. And in the case of sugars, you use trimethylsilane. You react that reagent with sugar. Every one of those free hydroxy groups around the sucrose pick up this volatile molecule. And lo and behold, you have your compound in the gas phase. What types of analyses are done? Really, really broad. It is a widely used technique through foods, through health, in all kinds of areas. We want to separate something, you can make it a gas. It's one heck of a good technique. And these are just some applications for foods, fatty acids, cholesterol, solvents, water, alcohol, pesticides, PCBs, kind of take your pick. I'm not going to go through all of them. And so it's, like I say, a very, very broad technique. I work with it in foods, obviously, but you go through a hospital, you go through other research facilities, these things are around because they're really, really useful. So what we typically do is, if the sample happens to be liquid or solid and it will vaporize on heating, we simply inject material into the hot inlet of a gas chromatograph, and poof, it becomes a vapor that then gets separated. So if it is a vapor, obviously you just take a syringe and squeeze it in. If it's not a vapor, it gets vaporized in the injection port of the column. And then as that gas is moving through the column, so it's simply your analytes move with it. They have very varying affinities for the solid coating as they're going by. This is in a tube that's got a coating. Gas phase going through with your analytes, and the analytes will have some affinity for the coating, some affinity you want to move with. So basically, you accomplish the separation in that manner. These are the parts of the system. Float, your carrier gas. So we do have our gas cylinder over there, and we'll talk about what is in that, or what kind of gas and so on. Of course, that's a high pressure tank over there. We need some kind of a flow controller so we can control how much gas comes in, how fast our mobile phase moves through the column. And then it goes through a detector and out to typically the atmosphere. But we're talking about micrograms, nanograms. It isn't like we worry about it from a pollution standpoint. And so these are the parts we look at. There's a figure up there that shows kind of two peaks. Okay, and these would be the compounds as they elute from the end of the column. They go into a detector, they get detected. Numerous kinds of detectors. It depends on what you want to see. This is then a little more, I don't know if you'd say picturesque, but a little, let's say a little more detail on it. And so we kind of go back over here. So we have our carrier gas, that's our mobile phase in our chromatography. Most of our gas chromatographs are set up to have a flame ionization detector, meaning whatever comes out of that column goes into a flame and gets burned. And then that burning creates ions, it measures the ions, and that measures how much compound came through the column. So the air and hydrogen are here just to have that flame so we can burn them and see, measure what we got. Here's our carrier gas that could be called a mobile phase or carrier gas. And it comes through some flow controllers so we can, get the right gases going to the right place in the right quantities. And so it comes over, we're going to go through this in detail, but there's an injection port up there. So we got our carrier gas, our mobile phase coming in. This comes into our column, and we can actually take a syringe up there and inject our sample. Right where it says injector's port, we go right through a septum and make our injection there. It's hot. Your sample gets vaporized. A column, and there's actually a flame up at the end of this column. That's looks like a candle. And so that's where your samples are burned and measure the ions that are formed. So it's really a simple technique. Then, you detect simply the ions that are formed. If you're just running hydrogen through the system with no sample, no ions are formed. Burn up a sugar, ions get formed. Burn up a fat, burn up anything else, ions formed. So a rather simple technique. These gases are high purity gases. Talking about the mobile phase, what's moving through this, your sample through this system. That's a mobile phase. Helium is traditional. That's expensive. That's extremely expensive. And alternative is hydrogen. Sorry, guys, we don't get off early. He's got a charger. Thank you. And so, okay, these are high purity gases. Sometimes people think, oh, the welding shop down there, they have hydrogen. Oh, they have oxygen. You need exceedingly high purity gases for this. So it doesn't get confused between what's burning in your mobile phase and what's burning in the sample you put in. So typically we use hydrogen, like I say, just simply because it's much cheaper and it's just as clean. We don't get any artifacts, any crud, coming to the system from that. And so that's our one gas is our mobile phase. And then I said we're going to burn these. Well, we need something to burn. And very commonly it's hydrogen, well, as a part of this system, and also oxygen. So we have air and hydrogen, and we will burn the sample there. So that's where we burn and get our ions being formed. We have to control the flow of these gases through the system, obviously, so we can get a flame burning, or so we can get materials moving through our column. And so we use different gas regulators. And so that can regulate the pressure, basically, of the gas coming into our system. And these, again, are sensitive precision instruments, not, again, welding or any other use. They are precision instruments that come at a fairly decent cost, unfortunately. So we can not contaminate the sample with our pressure control systems. They are good stainless steel, not welding quality, but equipment instrument quality. So looking a little more at the parts of these systems, we will start off with the injection port and kind of go through the parts as the sample moves along. So this is our injection port. So that's where we have our carrier gas or mobile phase coming into the instrument. So that coming in from your left is coming in. So that's our hydrogen gas. The flow actually, some of that gas goes straight across where it says purge gas. And that's simply a small amount of gas is always coming across the top as purge gas. And the reason for that is keeping everything clean. So you don't want anything to build up, any degradation products to build up. So we keep the system clean with that purge gas. And there is a septum on the top of that. We could use some kind of a pointer, but anyway, there is a way to enter. You'll see this whole tube. And so you would take a syringe, go down through the top, and make your injection into this part up here. So there's gas coming across, there's gas coming down the system, and it comes down the system, and some goes back out, and some of it that comes down here goes into a column and gets separated and measured. So again, it's just basically reducing the sample size. Your injection's about 1 microliter, and that's a lot when it comes down to the system. And so we've got to have some way to reduce that so we can detect it or be able to measure later on. So that's a really important part of the system because there are seals down here. You don't maintain things, and that seal doesn't get changed fairly often. Okay, you're going to have a leakage out here, and so much for your sensitivity. Up at the top where you take that as your syringe and go down and pierce that also. Do that a few times, and again, you have another opportunity for this gas to leak out. So again, this kind of maintenance, we need to replace particularly those 2 seals up there. And actually where you make your injection at the top going down, if you've got crud in there, it's not just what your analytes you want to find, but you find you got a little bit of sugar, you got a little bit of protein, you got a little bit of something else in there. That also then gets charred in the middle, and you start building up garbage in the middle. And so anyway, this needs maintenance. It needs to be kept clean. It needs to be kept from leaking if you want to get decent results. So that's the injection port. There's several different kinds of injection ports. We'll go through each of them just very briefly to give you an appreciation for what they are. So the split, so that means you've got the syringe, you take that syringe, you put it into the instrument, okay, push the plunger down, poof, it explodes, so to speak. And then you only take a small part of that and take it into the column and into the detector. If you put much material, it loads the column, overloads the system. So typically you work with nanograms, picograms, actually going through that column and getting down to the detection area. The rest of it actually just goes off into the room. And so, kind of like I say, evaporates and gets put away. So only a portion of your injection goes onto the column. And like I say, that keeps us from overloading the system. It's extremely sensitive detector. And so that's very common means of injection to split. If you're really looking at trace components, you're looking on the parts per trillion or lower, then you start saying, okay, I really don't want to have some of my injection be split off and chucked. I want the whole thing to come down the system. And that's where we get a splitless detector. And so everything you put in the syringe and you inject, it goes on, and that'll show up later. So a little more detail on that. So split, only a portion goes on the column. Splitless, everything goes on the column. And actually, there's some other options. One of them is an on-column cold injection. maybe you're working with something that's really heat sensitive and you don't want to stick it into a 200 centigrade injection port. Well, okay, so you can have cold injection ports too, and that's on column. So you don't have that, like say, injection port splitting up there. You don't have the heat. You simply have a more direct inlet to your column. And so sensitive materials, thermal degradation, chemical reaction, okay, a more gentle system. There's other alternatives programmed in temperature. So you make an injection that's cold, but then it heats up very quickly. Can go like 100 degrees centigrade in a couple, 5-6 seconds from room temperature, probably less. And so we can do, there's some different ways around this, but again, your workhorse is really the split at the top. And that's 99% of the type of inlet that you have when you're doing gas chromatography. And this is again showing an example of that and the flow. So if you take a look over here at the system, we've got on our far left, we've got a turbo flow. We've got 54 mils per minute as an example of gas coming into the system. You make your injection, but let's kind of look at the gas flow first. So 54 mils per minute, you've got 3 mils per minute that are being just swept off the top and emptied into the room. They're just keeping things clean in a sense. So let's keep some gas flowing here because you're making injections. When you make an injection, all of a sudden up there, that goes poof, and some of that will go down there, which then crudds everything up. So anyway, the 3 mils per minute up there is just keeping flows going and keeping the system clean. What you're really interested in is what comes down this direction. And you kind of look at the flows on this. There's a small part of that injection that actually makes it onto this column. So if we have 54 mils per minute coming in of this gas up here, you make your injection, only 1 mil, 1/54th of that ends up going in this column. And this ends up going, of course, through separation and detection that we'll see later on. So you're throwing away over 50, milliliters per minute and keeping 1 mil per minute of what you injected. So it's a splitter. It basically reduces the amount of compound that you have, because this is a tiny, tiny column. I'll have to bring an example for you next time. And so again, you don't have much capacity. You've got to keep concentrations low. You have a heck of a good detector, so it doesn't really hurt you. And so the system comes here. This 50 mils per minute just goes out into the room. 3 mils per minute goes out into the room, and 1 mil goes through your analysis, actually. So it sounds wasteful. Anyway, that's a split injection. This is a split less injection. And in that case, our system flows are really quite different. Over here, again, we've got the same injection port, 54 mils per minute. But what we have essentially is a large flow up there. It says 3 mils per minute septum flow, but it's also much of that 54 mils per minute. So 54 mils per minute, about 53 go right across the top. So it goes poof, but then gets pushed into the column. So instead of going poof and getting split out, poof, it gets pushed onto this. So we can go ahead and get more sensitivity out of the system. This is the last one we'll look at. The first two are most common. So this is a last injection port, and really very, very different. Supposing you're working with chemicals or compounds that really aren't very thermally stable, and we don't want to inject them into 200 degrees centigrade and let them go poof. Okay, let's go ahead and use a much more gentle system. And so in that case, you actually take your syringe, and you see it up at the top, and put it down into somewhere around there. And then you make your injection down here in the column. So you're actually injecting your liquid into the column, and the only heat it sees is column temperature. So it's just for things that are just very, very heat sensitive or heat labile. So those are the kinds. From that, so that's our poof, and here comes our sample. What is it? Where does it go? It goes into the column, GC, gas chromatographic column. And we should again have visual aids here, but they can have 20-meter columns of glass, and the glass is wound in a circle, which you can say that's glass. It's a very strong glass and a very, very thin glass. So as it's bent, it doesn't have much shear stress. So this is typically your workhorse. It's just a little bit smaller than the picture shows here, but that's almost the actual size. And like I say, that can be 20 meters, 50 meters, 100 meters long, wrapped up in there. And so there's our columns. They, for the most part, are simply like this. You can have columns here that have actually coatings on the inside. And these, these are fairly substantial coatings. This has a very, very thin film of the stationary phase. So you have a difference. You can see some of these, but these again are the workhorses that you see in the lab. There are fused silica as the material, very high purity, strong, inert. The inside diameter of that column will range from anywhere from 0.1 millimeter to 0.53 millimeters. And so again, we tend to work around the 0.3 millimeter size column. So that's the outside diameter of that column. And so with 0.3 is, well, 0.25, 0.3 is the most common. The length, that may be 1 meter of column. It can be 60 meters of column wrapped up in there. And so length, how difficult is your separation? You got an easy separation, doesn't take much column. Doesn't take long to get this gas going through 1 meter. Quick results, rapid data. If we're having a tough separation, okay, then we need more column. Then we go with longer columns. There's a coating inside of that glass column. That's our stationary phase. So your analytes that just got vaporized come down into this column, and there's the coating, and that coating interacts with the analytes that you're looking at. There aren't a lot of coatings that are actually used in the system. What do we have? 1, 2, 3, 4, 5, 6, 10, 11, whatever, something like that. And they're names, if you want to call them that. We call them, you have an OV1 column. How about an OV225 or whatever? So this refers to the meeting, the actual material inside the column where we get our interaction. And each of these materials, the coatings, really range in polarity. We're doing a polarity separation. So analytes coming through here, it's moving through that column. Does it want to dissolve in that coating or not? What's the polarity? The other thing that works for you is also boiling point, because you'll start that column out commonly, something like 40 degrees centigrade, make your injection, things start moving, but then you start warming that column. So that column is actually temperature programmed. So things you injected, volatile things will get moving on their way, non-volatile things will get moving on your way when you start heating that. And so you may go from ambient, for that matter, column injection to 200 degrees centigrade. And that may take a fairly short time. It depends on what you need. So we take advantage of both the polarity and boiling point to get our separation. There's no other analytical technique that challenges this methodology for resolution sensitivity. It's one heck of good technique, broadly used in the field. So, okay, we make our choices here. If we've got polar compounds, we use a polar column. You have non-polar compounds you want to measure, use the non-polar phase up at the top. So generally what you do is you look in literature and say, okay, somebody else did this for separation. What did they do? What were their temperatures? What was their column? What were their conditions? And you simply do what they did, assuming they did well, right? Things correctly. And how do we know what column to use? So we've got different lengths, different diameters, different coatings. And actually, there is a lot of published information on this technique. And you start saying, okay, I have this compound, this compound, this compound. You can actually look that up in our Kovacs indices is kind of the book or the summation of this retention indices. You can actually find what's the best material, what's the best column to use for your separation. So it's this is certainly available. Look it up. What do we need? Most commonly, we go to journal articles. If somebody else has done the separation, most separations have been done by now. So you don't very commonly run into something nobody else has ever done. And so very commonly, you simply go to a journal article and say, hey, what did they use? How did they do it? And you set up your system to be the same. Because they typically will publish, a picture of the results of what we call a chromatogram. And then when you do your separation, you can say, oh, okay, that looks like mine. Yep, that came off there and so on. So feels kind of good or comforting. If, well, journal articles in-house, is somebody else working on that? So again, some other things that you use in this. Well, intuition, like structures, if you're working with a nonpolar compound, nobody's ever done it before, you take a nonpolar column. You want an interaction between your analyte and the coating on that column. And so you can actually make your own judgment about what's the best column by kind of looking at your properties of your analyte. But again, it's simple to find it typically in the literature or, like I say, in-house. If you'd be really unique and have a problem nobody's ever looked at, okay, then you kind of, play it by ear. And you always start off with a non-polar column. You run them from ambient up to 250 degrees centigrade and hope someplace in there between 0 and 250 centigrade, your compounds make it through that, phase and make it out for analysis. So what kinds of chromatography do we take advantage of when we're doing gas chromatography? And so these are the four bases. Adsorption, your column is a coating inside, but it's a really, really thin coating. You don't get absorption into that coating, you just get a surface interaction. So you can have adsorption as a basis of separation, looking at how your analytes absorb into that surface. Molecular exclusion, you can do separations based on the size of your molecule. Is it a little molecule like water? Is it a big molecule like a carotenoid, called a pigment? So again, you can separate based on molecular size. Partitioning, that's where you do have this liquid coating inside your column and it's fairly thick. So it's going to dissolve in it and move back out, dissolve in and out. And also volatility. You kind of keep that in mind that we do temperature program these things. We start off maybe at 50 degrees centigrade, something like that. And then some compounds will be very volatile at 50 degrees centigrade. They'll want to move on their way. Others, no, I'm still staying a liquid. Hey, So you then temperature program gradually. And so basically your analytes get kind of released or volatilized into this moving gas, and we get separation based on that. And yes, we do temperature program these ovens and columns just for that reason. You can start off at ambient for that matter. Well, we can actually go below ambient, or you can then you can keep on heating as you go up. These are kind of the workhorses. Most commonly, what coatings are used inside of your columns. Nonpolar, a DB1, that's the most nonpolar column. So tremendously hydrophobic. Okay. Semi-nonpolar, that sounds like an oxymoron. But anyway, you're kind of middle of the road. It's not nonpolar. It's not polar. It's someplace in the middle of that track. And then you get down into nonpolar, and that's the silicone-based phases. And every company that supplies equipment to you, materials for chromatography, they have, of course, all different columns, different coatings, different lengths, and so on. And they all put their trade name on it. And so you have an OV1 from this company, an HP1 from that company, an EX from this company. But the numbering, they're typically, columns are numbered in a sense, 1 to 50, 100, and so on. That's the same, but anyway, it really depends upon where you buy, what the name of that coating is. And there is a column oven in there. So we get a separation based on solubility as it goes through column. We get also separation based on volatility. And so that column may, like I say, start off at ambient, and some things aren't very volatile. Some things aren't going to go into that moving gas phase at, ambient temperature or even slightly higher. So what you do is you start off at low temperature, let those things that are volatile start on their merry way, and then start heating it. So temperature program that inlet, so you can get more and more heat, more compounds evaporated. And these are ovens. I did have a grad student once heat their lunch, and that wasn't appreciated by some. They are scientific instruments. We don't put our lunch in them. Hot dogs, no. So, but they are controllable from -60 to 400 degrees centigrade. So that column can be put under quite a range of temperatures. So you're taking advantage of volatility, boiling, keep moving out in the gas phase. Detectors, okay, so we've got our sample, we injected our sample, we got it going on its merry way. It comes out, elutes out, and hopefully it elutes all by itself, so it's a pure, pure compound. And then something has to measure it. You need a measurement. And there's different methods for detecting compounds too. And we'll go through some of those. But the whole goal is to take somehow the presence and quantity of an analyte and turn it into electronic signal. So that's what we'll kind of go through and show. The ovens, yep, okay. Controlled from -60 to 400. Okay, we did that. Here's our column polarity. We've also given some examples of that. The DB1, DB5, Carboax is the Carboax, the polar phase. The DBs are the non-polar phases. What other things do we have going for us? And we look at separation, so temperature, volatility, affinity for that coating. So what can slow down, what can make separation? We think about solubility, like I say, and temperature, but there are different methodologies we can use for separation also of this mixture of analytes you just vaporize. You can actually use not a column that is a surface and it dissolves in the column, but simply you get an interaction with the surface of the column only. And so adsorption, we look at analytes absorbing onto the surface of an inside of a column. And so your column surface is more important or very important. We can actually take advantage of size, your molecular size too. If you can put a packing in there, and that packing doesn't have a hole through it. Most of what I've been talking about, it's an empty column with a thin coating around. Here now I'm going to pack the whole darn thing with a material that has different size pores. And so your analytes, if the analytes are fairly small, they can maybe enter this particle inside this column and can wander around, eventually come out, go into another one, and so on. Another one says, there's nothing here. I'm too big. I can't get in. It goes through. And so you're separating molecules based on molecular size. So we base it solubility, polarity, volatility, and yes, the idea of size separations. Most of what we do is more partitioning chromatography, putting a coating on the inside of that column and looking actually at our analytes dissolving in and coming back out. So number three is the number one factor, but again, vapor pressure does play a role. You'll almost always temperature program a run. Like I say, you may start off at 60 degrees centigrade, go up to 250 degrees centigrade on these columns. And so that just simply takes advantage of volatility of your compound. So you almost always take advantage of 3 and 4. Number 1 and 2 are very specialized. 3 and 4 always come into play. And so here's our column coatings, stationary phase, what we call it. The nonpolar, I think we've already kind of mentioned that, is the DB1. Semi-nonpolar, DB5. Polar carboax. I don't know how that got its name, but anyway, well, we get generally abbreviations like DB, something else, something else. Carboax, for one reason, uses its full name. So those are kind of nonpolar, semipolar, polar. And they each company does label their products differently. So there is a DB5, there's an HP5, there's a, depending upon what the company wants to put on for abbreviation. So you'll find some confusion there also. You say, is a DB5 the same as an HP5? Yep. One's made by Hewlett Packard, HP. Okay. That one's DB. I don't know who DB is, but anyway. Just a little bit about columns. And yeah, we usually do heat the columns, and temperatures already mentioned goes from -60 to 400 degrees centigrade. Getting -60, of course, that's where you inject liquid nitrogen into the column. And so you can actually cool the whole column area, oven area, with liquid nitrogen. So if you're looking for things that are extremely volatile, you'd probably be wanting to run those kinds of temperatures, -60 and so on. Most of the time, you work closer to ambient temperatures and up from there. And I said the purpose of detectors are simply to turn some quantity of material into an electronic signal. So simply, how do we go from physical particle into an electronic signal? So that's our goal, and that's where we get our sensitivity differentiation from. There's also different detectors. You've got different injection ports, different columns, and different detectors. And we'll spend a little bit of time looking at detectors as well. But this is what you'd like to get out of this. So here's your chromatogram. There's a solvent. So your sample was in a solvent, so that comes off first. You use very volatile solvents so they don't get in the way of what you want to measure. And so there's our solvent, and here's the first peak, 1.413 minutes. Next one dilutes at 1.769 minutes. And then we've got, of course, output here. And those times are useful to us. They are being separated mainly on the boiling point basis, so they are useful information. We'll show why a little bit later on. So we've got our injection, we have our separation. Okay, now we got to detect whatever. So this is the turning compound into an electronic signal. And there are several different kinds. There are workhorses. The workhorse is a flame ionization. So you simply burn whatever comes out of that column. It goes into a hydrogen flame, get burned, ionized, and you measure the ions. Okay, that's a workhorse. But again, there are several different approaches, and we'll just simply mention them now. Thermal conductivity is one detector. It's probably the oldest detector that we have, and it's they're all unique in how they work. So the fact that it's old doesn't make any difference. It's a technique that's still used a great deal. And so what we've got is our column effluent is coming out here. So our column is over here. That column is gas coming out of it, carrier gas coming out. That goes up to the middle of the system, and comes out that direction. So we've got actually materials going through that column as we take a look at it. And this, well, I didn't do that right. Can we start over on there? Oh, thank you. Okay, that's our analytes coming out. The orange, the red parts. Okay, so they're making these molecules big and round. But anyway, the idea that okay, that's what's coming in here, and the effluent from your column, all that carrier gas, mobile phase, and your analytes are pushed through this and out. So they're coming here. This is just an electrical filament. And what the machine is doing, it's monitoring the temperature of this. So it's at a certain temperature. And if there's nothing coming through here, no compound, there's really not much cooling event. But okay, now we have a compound coming through. Well, these molecules are going to cool this more, and it's going to change resistance of the wire. And so what they measure is resistance of this wire and how it changes with analytes. So it's called a universal detector because actually everything, anything will affect the cooling of that wire. So it doesn't matter if it's an aldehyde, a ketone, a sugar, you name it, it's going to affect this. So our other detectors tend to be specific. They are better at some things than other things. But okay, universal detector, not overly sensitive, but the idea that they basically will detect anything is interesting. They find their biggest use probably when we look at measuring various gases, maybe doing a separation there. So anyway, finds application. So this is as the machine runs, this is as there's some analytes in there, the blue triangles that will cool differently. So universal detector, not overly sensitive. That's a problem. So sensitivity, 10 to the minus 7th grams of material going through the machine. 10 to the minus 7 grams, that doesn't seem like a heck of a lot, does it? And this is horrible sensitivity, compared to the other techniques we've got. The machines do have sensitivity and tremendous sensitivity. So it's the poorest in terms of sensitivity, but has the advantage of it detects anything. So if we were going to be looking at gas packaging foods, we're going to go ahead and put this package in a nitrogen environment. Okay, we're going to see what happens to our shelf life. If it's in an inert environment, you can go ahead and make up your product, put the gases in there, and then periodically you come in and poke the package, drop some gas, and analyze that gas, because basically some of those analytes that are given up, oxidation products, whatever, will influence your run. So nice detector in terms of universal detection, anything it will detect. So not specific, to detect water, gases, you name it. Linear dynamic range is poor. Response easily becomes nonlinear, and the dynamic range, your sample composition can change by 10,000 and still be fine. And we call that poor because we like to see even better than that. Concentration range may be quite different. So not overly sensitive. That's okay. But like I say, universal. That's really an advantage. So you detect gases, you detect anything you really want. This is the workhorse. If you go down to our labs down there in food science, this is generally what you'll find that's hooked up at the end of a column. And so it's a flame ionization detector. So this detector, your effluent from the column. So as things come out the column, they end up going up through the flame, and as the analytes and as the carrier gas goes through that flame, they form ions, and flame burning generates ions. the more compound, the more ions, obviously. And so then right above, that is supposed to be a flame up there. It kind of looks like it, doesn't it? Candle, anyway. So there's the jet and the flame. And so that flame tends to give off ions. It's ions that are formed in the flame. And so that kind of tube that it's running up is basically measuring how many ions are formed. So you're measuring what ions are formed as these compounds are burned. And so that is, like I say, that what we find most often used in the laboratory, because basically any organic material you will measure, you can measure. Can't measure water, can't measure air, but you can measure any organic material. And so specificity, 10 to the minus 12 grams per second. And there's this grams per second because you're kind of looking at the amount of ions that are formed as a function of time. You want to generate a peak. So 10 to the minus 12 grams is really quite good in terms of linearity. We don't do too many things where our concentration changes by 10 to the 12th. So good sensitivity. It does organics, very linear. That's very good. The 10 to 6, 10 to the 7. And like I say, so specificity, sensitivity, linear range are really what you have going for you in this system. This electron capture detector, this is a detector that certainly finds use. It's, again, unique in what and how it works. Basically, in this case, we actually put a coating on the inside. So we've kind of got our column in here, we've got our makeup gas, then we have that chamber with this rod sticking down. And so all around that chamber has a coating that's giving off electrons. And those electrons that it's giving off get collected on the anode, so coming down there. So we've got this constant flow of electricity between the two ions going back and forth. And what happens when you put a compound in the system, it'll interfere with those ions. It'll absorb some of those ions. And so that's what are we supposed to leave? We're having fun. Okay, well, sorry about that. Maybe I can pick it up next time. Okay, okay. I will pay attention to time. Oh, are we just a couple minutes off?
Yeah.
Okay, good. Then we'll go. Okay.